All right, so today our dream seminar speaker is Professor Ian Mitchell, who received his PhD from Stanford in 2002, co-supervised by Claire. And then he did a one-year postdoc here with Shankar. He's currently an associate professor of computer science at UBC, the University of British Columbia in Vancouver, Canada. Ian's research interests include formal verification, control of cyberphysical systems, and assistive technology. And he's the author of the level set Toolbox, which many of us use on a regular basis. So today he'll be talking to us about some of the challenges of verification. And so please welcome Ian.
Thanks, Mo, and thanks to Claire and Rujna and Murat and I guess Shankar for the invitation to the Dream Seminar. I have here, it's hard to tell, but I have a cup from the year that CPS Week came to San Francisco. All the writing has worn off because I bring it to all my conferences as a place to store my tea. I'm not going to talk today about the level set toolbox. I'm going to talk about some other stuff, but I'm always happy to chat about the level set toolbox if anybody wants to ask any questions about it. I'm hoping that we'll make some progress in terms of adding some new features to the level set toolbox soon. Claire was part of this. There was a proposal to get an IPAM workshop that was unsuccessful for a year and a half from now, but there's a workshop in Linz at the end of this month, and then there's another workshop in Rome next summer on new techniques for Hamilton-Jacobi equations and control. So hopefully there will be some new results at those that I can implement and feed out to the community. There's been a sort of a lull over the last 5 years, and I'm hoping that it looks like there's some new results that look quite appealing coming from a number of different groups. So anyway, what I'm going to talk about here is, let's say that you'd actually computed a verification. What do you do with that? And in particular, one of the strengths of the level set method and the Hamilton-Jacobi approach and some of the other approaches that I've been working on more recently was that it tells you that your system is safe, that there exists a control that will keep your system safe, often robust to some kind of disturbances. And that's all fine and good until somebody says, okay, so what is that control? And what are you going to do with it? What are you going to do with the system when what the system is doing is not that control? And so this talk sort of looks at some of the questions that surround that. So just to get started, formal methods, I think everyone here is familiar with this idea that we're going to try to generate some kind of proofs or some kind of mathematical rigor in the development of our systems and prove that they satisfy some conditions. And one of the most common conditions that you would like is safety. So there's certainly been a lot of work recently on more complex conditions from temporal logics, but I'm really going to focus on safety. And the tool that I'm going to use are things around reachability. So we're going to look, for example, at the set of states that can hit some target set under some set of dynamics. So here's our dynamics, green arrows, and here's the backward reach set. And the conclusion that we're going to draw is that the rest of this is safe under appropriate control. And for a lot of the rest of the talk, I'm going to talk about that question of under appropriate control. So that's an outline of my talk. And I find myself suffering from an inability to produce talks in a single format anymore. Because, gee, Beamer is nice, and I love writing my talks in LaTeX and copying stuff over from papers directly. And I am collaborating with a bunch of people in the med school, and they will never, ever, ever think about LaTeX. And so I have a mixture of slides. And so for the first few slides, I'm going to switch over to a Beamer slide deck, and then I'm going to come back and show you some stuff in PowerPoint. So where is it? There it is. So here's my Beamer slide deck, and much thanks to Shahab, who was a postdoc here for a little while, who helped me put this together the first time that I did it. So I'm going to talk a bit about the constructs that I'll be using, some models and algorithms, and then a particular context where the stuff that I've been doing for years really doesn't apply to real cyber-physical systems, and that's cyber-physical systems under the sampled data model of time, and then something I'm calling the control filter hybrid automaton, which is a way of using that information from the sampled data reachability calculation to try to ensure safety of, in this case, a quadrotor flight envelope maintenance. And so first with the constructs. So I talked about reachable sets. In fact, a lot of what I've been doing recently has used the constructs from viability theory, the invariance kernel. So this is the set of states that no matter what you do, you will stay inside some constraint set. And the constraint set here is S. And so the invariance kernel is all of those initial conditions that give rise, where all the trajectories they give rise to stay inside this constraint set S. And that's fairly straightforward. The viability kernel is the opposite quantifier there. If there exists a control or exists a parameter that will get you to stay inside this constraint set, then you're part of the viability kernel. So the viability kernel contains the invariance kernel, but these are two different things that we might want to do with our uncertainty. If this constraint set represents the set of safe states, then the invariance kernel, you can think of it as treating the inputs or the parameters in a worst case fashion. So this guy is not part of the invariance kernel because there exists a trajectory that leaves the safe set. And it is part of the viability kernel because there exists a trajectory that stays in the safe set. So best case and worst case. I try to avoid that terminology a lot because what this set represents may depend on the problem. It might be a good set or it might be a bad set, and then the meaning of best and worst case changes. So the invariance kernel, the viability kernel, the capture basin, which is essentially a viability kernel used in an until fashion. So we need to stay inside the constraint set SC until we hit the target set. And after that, we don't care. And we must hit the target set. In this case, we're doing finite horizon, so we must hit the target set within that finite horizon. And finally, I'm going to use a construct called the robust reach set. This is the set of states that give rise to trajectories which will reach this terminal set no matter what after a fixed period of time. So this is not a converse of the viability kernel because this is at a fixed period of time. So you start at time t sub s, and you must be within the set S at time t sub f, not pass through that set on the way. And the reason we use this is we use it in construction. I should point out that this is a weird set in the sense that you can't just take the union of these sets and get the tube. And the tube is, in fact, the converse of the viability kernel. It's typically what you want. In most actual application domains, you want this robust backward reach set, or sorry, reach tube. So the set of states where you will pass through the target set, the set S, at some point in time. But in this case, I want you to land in the set S exactly at that point in time. And then the discriminating kernel. And this is where you've got both quantifiers. So there exists a control that, despite all the disturbances, will keep you inside the constraint set. And I don't have a good way of drawing this. I've tried for like an hour. I can't figure out how to draw it, but we basically have both types of inputs. We have, if S is a safe set, we have some inputs that we're treating in a best case fashion and some inputs that we're treating in a worst case fashion.
Can you show that the negation of that there is never, you can design a controller?
If you were calculating this thing exactly, yes. But typically we're approximating it in some way. And so we end up with necessary or sufficient conditions, not both. So yeah, if you solve this thing exactly, then you would know that something has failed in the formula.
Cases where you probably can never
Solve this exactly?
Yeah, exactly.
Oh, yeah, absolutely. And in fact, there are cases where I believe there are some ugly cases where you can show, for example, that the boundary of the set is not reachable, but the open set is reachable. And so there are some mathematical details here that come up when you're working with discriminating kernels, having to do with the ordering of these operators in continuous time, that gets tricky. Okay, so there are lots of ways, or several ways, of calculating these sets using non-parametric representation. So grid up the state space and approximate these sets. For example, using level set methods, using Patrick's algorithms that Patrick developed and extended, and apparently he's still extending them. He's still puttering away on them. But the problem is that the complexity is exponential in the state space dimension, so you can't really do more than 4 or 5 dimensions. So on the other hand, we have parametric representations. So this is where our sets are going to be represented by something parametric, like a polygon or an ellipsoid or support vectors or support functions or something parametric. And we have those, and they work great for reachable sets, but not for viability kernels. And there's implementations available for these things. And so this was work that John and Shahab worked on when John was a master's student up at UBC, was basically taking these parametric reachability algorithms and applying them to viability problems for both continuous and discrete time. And it's not a complicated idea. So you have some constraint set. You're going to erode it by a small amount, this computational step rho, so that you can take into account the fact that we're discretizing time. And then we're going to calculate the backward reach set, intersect it with that eroded set, calculate the backward reach set, intersect it with the eroded set, and so on. And you end up with an approximation of the viability kernel. And all you needed was the ability to be able to, or you just need to calculate backward reach sets and intersections. And we can do that with ellipsoids, for example. So we can calculate the maximum volume ellipsoid within the intersection of ellipsoids, or more generally convex sets, using a convex optimization algorithm. And we can calculate an under approximation of the backward reach set of an ellipse. We can calculate a collection of ellipses which under approximates that backward reach set. These are all approximations. The set of ellipsoids is not closed under these operations, and so we're going to, at every step, sort of under-approximate along the way. But we can do this for the robust case with both control and disturbances, and we can do it in continuous or discrete time. And for example, this is a 4D problem that Shahab solved at 5.5 hours using level set methods. That's the black shape. And 10 minutes using ellipsoidal methods, piecewise ellipsoidal methods. And you can see it's okay. It's not perfect. There's a gap between the green and the black right there. But it's way faster. And then 7-dimensional problem, which is just totally infeasible for the Toolbox. And so you can solve this in 15 minutes using these ellipsoidal techniques. Okay, so these techniques work in either continuous time or discrete time. And the question is, what do you do when neither of those models make sense? And where does this come up? So here's a typical cyberphysical system. You have some continuous plant. You have some discrete time controller implemented on a chip. And in between, you have time sampling sensors and zero-order hold actuators to actually map between these two spaces. And so if the time constants of the plant and the cycle time of the controller, if the time constant of the plant is much larger than the cycle time of the controller, this is fine. Go ahead and use continuous time or discrete time. It really doesn't matter. If anything happens in the plant and you've decided to use discrete time, this guy's going to notice that something's happening in the plant and be able to respond to it in your discrete time model. If you're using continuous time, the same thing is going to happen. You're not going to have much of a delay around this loop compared to the dynamics of the plant. So everything's fine. Now, if the dynamics of the plant are way faster than the controller, you're probably hosed. Your controller's not going to be able to keep up. So the interesting case for me is when the dynamics of the plant are of the same order as the dynamics of the controller. So things are happening in the plant, and the controller has to be aware of the fact that things will happen before it gets its next opportunity to adjust the inputs. Okay? And so unlike a continuous time model, we cannot change the feedback whenever we want. We can't have, say, a switching surface and say when the plant state hits that switching surface, now we're going to change. Because we might be between sample times. And so by the time we notice we've hit the switching surface, we're going to be beyond the switching surface. Or we're going to have switched too soon. And likewise, in a discrete time model, you're ignoring what the plant's doing in between sample times. So in sort of the worst case situation, you'll sample the plant before it becomes unsafe. It will be unsafe between sample periods, and then at the end of the next sample period, it'll be safe again, and you'll say, oh, everything's fine. I just didn't notice that it flew through that window. So that's the sample data model, is we want to take into account the continuous nature of the plant and the fact that the controller can only respond at certain times. So we do that with a piecewise constant control. So we're going to have a feedback policy at the sample times. We sample the feedback policy, and then we apply it over the entire next sample period. So that's the zero-order hold, is that we apply it over the whole sample period. And this is the sample-based sensors. And I'm just going to talk about the case where the sampling time is fixed, but we can handle timing jitter. So if the sample time varies a little bit. And if we have a disturbance input, like here, we're going to allow that to do whatever it wants. So we're assuming the disturbance input is not time sampled. It can just do whatever it wants for sort of safety. And the way that we do this is we essentially blow up the state space and fix the control values, calculate a reachable set in this higher dimensional state space with the control values fixed. So the U values have a dynamics of 0, and then we're going to project everything back down into the appropriate spaces. Is the way that the algorithm works. So this only makes sense if you can do high dimensional spaces. But we can because we have these ellipsoidal algorithms. So here, for example, is a model that Shahab did before he headed off to work at ClearPath of a simple 3D quadrotor problem. And so here's the safe sets, the viability kernels in green here. And the other thing that this algorithm gets you is an ellipsoid that describes the set of safe controls at every point in the state space. So here are slices of that set of safe controls at various points in the state space. And so these are the states, x1, x2, and slices in x3. This is U. These are the possible control values that are good. And to figure out what control values you can use, you figure out which x3 value you have, and then the slices show different x2 values, and then you pick an x1 value, and that gives you a range of values that are valid for you. So at any point in the state space, in this case a three-dimensional state space, I have a range of U values that I can use that are guaranteed to keep me in this green set. Great. So what do I do with that? This system was almost linear. There's one nonlinear term. We linearized that and then took the linearization error and treated that as a disturbance. So this is this analysis is for the nonlinear system by doing a linearization and then making it robust to the linearization error.
Have you done over approximation?
In the context of synthesizing a control, in the context of synthesizing the control for viability kernels, or discriminating kernels, we want an under approximation. We could do over approximations. There's all the algorithm works.
Can I just have like a reference publication we could look at?
This one is Automatica paper. Or sorry, this one back here was the Automatica paper. And then the sample data one was HSCC 2015. So the question is what to do with that information, with those ellipsoids. And so that's where this control filtering hybrid automaton comes in. And this is a paper that's going to appear in CDC. And for this problem, we decided to go after the capture basin. The algorithm is essentially the same. It just changes what you start with. Instead of starting with the constraint set, you start with the target set. And then the rest of the algorithm is exactly the same. At every step, you're intersecting with the constraint set. And so we're trying to calculate the sample data, finite horizon sample data capture basin. And we're going to make this perhaps unreasonable assumption that we have some kind of infinite horizon controller within the target set that we've chosen. So this is somewhat like a common technique that's used in MPC to prove infinite horizon stability of the MPC. You choose some target set where your linearization is extremely accurate and build a controller that will work within that target set. And then you use MPC and tell the MPC that it always has to finish its horizon inside the target set. And that's the same idea here. We're going to say, let's assume that we have a target set. We have a way of keeping the system stable inside that target set if we ever need to get to that situation. And let's build some system that guarantees that we can hit that target set over our horizon. Here's the algorithm. I don't want you to look at the details. You're calculating an invariance kernel and then you calculate one invariance kernel, a bunch of reachability kernels, and intersections. And then you do projections. And this will give you an under approximation of that sample data capture basin, and a different projection of the sets that you're calculating gives you an under approximation of the controls, the controls that are available to keep yourself safe. So that's basically what we get out of it. We get a set of states that are guaranteed to be safe, and for every state within that set, we get a set of controls that are guaranteed to keep you within that set.
Is there a way, if you had a more nonlinear system and you didn't want to have to linearize just once, is there a way to do that linearization iteratively so that at each step you're dealing with a linear system, but it may be a different linear system?
I'm working on that. It involves, it looks like you need to be able to solve some mixed integer convex programs, but it turns out coincidentally that we had somebody visiting UBC last week who's an expert on mixed integer convex programs, and he made it sounds like this is something you might be able to do. The problem is that you have to be able to show that it's not quite what you're saying, but you have to be able to show that you can move between these linearizations without the possibility of sort of escaping trajectories. So I think so, but I don't have any proof to back that up yet. So here's the idea. We're going to calculate this sequence of ellipsoids. In the end, it's going to be ellipsoids, but we're going to calculate the sequence of sets that are guaranteed to be safe. We're going to build a discrete automaton that goes into this blue box here, and this discrete automaton has a number of modes equal to the number of steps that we're taking, the finite horizon. And in each of these modes, you're going to be allowed to be in that mode if you're within the capture basin for that horizon. And because we're working with capture basins, you don't have any kind of semigroup property here. Your capture basins may not overlap. So it's not like the capture basins grow monotonically or shrink monotonically or anything like that. There can be states that are in capture basin I and not in capture basin I+1 or I-1. So we're going to have separate modes for each of these horizons. And within each of the modes, we're going to say, choose a U that falls within the set of safe controls U. And then we're going to say, I'm not showing all the edges here, but all the modes are connected to every other mode. And the key thing is we can show that the next mode, I-1, is guaranteed to be feasible. I can guarantee that if you choose this control, you will be in this mode. And so the fastest that you can end up here, forced into the target set, is the mode that you're in. If you're in mode I, you have at least I steps until you're forced into the target set. And once you're forced into the target set, you're going to have to invoke that stabilization, that infinite horizon stabilization controller in order to guarantee infinite horizon safety. So you don't want to be forced into the target set.
What is the trigger between those, between the
The guards on each of the edges is just the invariant of the incoming mode. So what we do in practice is we just, yeah. So once you compose this discrete automaton with your continuous plant, you get a hybrid automaton. Exactly, and that's where it goes with the control filtering hybrid automaton. Thank you for mentioning that. The control filtering hybrid automaton is the composition of this discrete controller with the continuous dynamics of the plant. Okay, so an example. This is a quadrotor model from Claire's lab, which we were working with, and Forrest Lane got the constants, characterized all these constants in here. And it's a longitudinal model, so we're not paying attention to yaw, and we're not paying attention to depth of the quadrotor. So we've got x1 is horizontal position, x2 is vertical position, and then the velocities in each of those two. x5 is your attitude, and x6 is your angular velocity here. And the only thing to note is that this input, the second input, U1, is your total thrust. The second input, it looks like it should be an angular thrust, a differential thrust that's turning you over, angular acceleration. But in fact, this is a little PID controller, or PD controller, that is so that U2 is your desired roll angle, rather than being an acceleration. Otherwise, the thing is uncontrollable. This is Forrest's approximation of your Vicon room upstairs. And this is Forrest's approximation of where he can stabilize the system with the LQR controller. And mostly these things are actually not too far apart, except down here. And this is angular velocity. We've got a very tight constraint on the angular velocity in the target set. So the LQR controller works over most of the domain except in the target set, except for the angular velocity. We want it to be almost steady when you turn it on. He just made up a controller, a stabilizing controller, and then he tried it out for a bunch of different states to see where it worked. And we don't have any. Linear quadratic regulator, right? Yep. I always think of it as being the Q and the R matrices. Linear, and then it has a Q and an R matrix. But so he's linearized the dynamics about in this range, and notice the nonlinear terms have to do with x5, and he said x5 is a very narrow range, and then he's built an LQR controller, and it seems to stabilize. I must admit that we have no proof that this actually stabilizes in this region, because proving it is kind of a reachability problem in itself. So we haven't managed to do that yet. But what we were trying to demonstrate here was the capture basin part of it, to show that we can demonstrate safety over a much larger set of states, just having this thing as a backup. And I'll show you right at the end that. So we need to linearize, because the ellipsoidal stuff is all linear systems. So here's the linearization. Here's a constant term, which is easy to factor in. And there's the linearization error. And this is the term that causes us all the problems, that one right there. Because x5 is near 0, so this term is pretty small. These two terms are very small. It's this one that causes all of our problems. But we're going to calculate the capture basins robust to the linearization error. So we are going to bound that error and then calculate capture basins. And to bound that error, it turns out we can't just flat out bound it. We are going to hybridize the dynamics. So we're actually going to linearize about 5 different operating points. And this sort of graphically shows you those operating points. So G is the force of gravity here. So the total thrust is always G plus or minus some small amount, so that we stay in the air. And then we're going to linearize, an upward thrust, a downward, allowing the system to go downward. And we're also going to linearize about slight tilts to the left and to the right. And we adjust, so to cover the constraint set, we use different ranges of this hybridization. So we end up with 5 different versions of the model, and we're going to calculate reach sets in each of these 5 different versions, depending on where the current state is. So here's the capture basin. The red box is the set that we'd actually like. That's our real constraint. We can't get that with an ellipsoid. In fact, ellipsoids are terrible at approximating boxes. In 6 dimensions, the optimal sphere inside a 6-dimensional unit box only contains 20% of the volume of the box. The corners of the box are enormous. And so this is struggling, and this is really the weak point of the ellipsoidal techniques, is if you're working with box constraints, it's a terrible way to approximate them. But this is what we're working with right now, because we haven't managed to extend John's work on support vectors, which would allow us to do more polygonal constraints. And so what we do is we build a couple of different constraint sets, 3 different constraint sets, and 3 different target sets to try to fill up a little bit more of that space. There's this idea of doing multiple directions, but it turned out I tried every other direction, and I never got better than this one. So I'm just using the one. And here's the final results. So we're not doing great in some dimensions. The green set is not much bigger than the target set. But in other dimensions, we're doing a little bit better. And in the critical dimension, which is x6, that's our angular acceleration, we're doing a lot better. So we've got a large range of angular accelerations that we can bring things under control. And the computation here takes about 15 seconds for 10 sample periods for each of these things that we're calculating on. And it turns out we've got 5 times 3, so 15 different combinations that we're working with. So it's less than 5 minutes to calculate these sets. And so we could do a lot more. So what are we going to do with that? Well, for the paper, my thought here was, oh, well, we'll just take this input, somebody playing with a joystick, and we're just going to look and see where's the current state, where's the user's input, where's the pilot's input, how does it compare to the ellipse containing the safe controls, and if we can find an ellipse such that the pilot's input is within that ellipse, then we're done. The pilot is doing something that's already safe. But if we find that we can't, there's no ellipse that contains the pilot's input, then we're going to have to do something. And right now, what we're doing is we're just clipping it. We're projecting onto this ellipsoid. We're projecting the pilot's input onto the ellipsoid. We do this for a bunch of different modes. And this is kind of heuristic, the modes that we chose. We said, let's try to increase our horizon a little bit. Let's try a few of these other hybridizations. Let's try a few of the other constraint sets and see what we can find. And the key thing here is that every one we try takes about 30 milliseconds to evaluate in MATLAB. We're basically testing an ellipse, so we're evaluating a quadratic function to see if the pilot's input is inside this quadratic function right now. And so we can test 18 of these. We had a 100 millisecond cycle time. So we can test 18 of these and still stay well within that 100 millisecond cycle time. So what's happening here, these are the states. And you'll notice here, in this region, you're very close to hitting the wall on one side. And so when the pilot tries to adjust the desired roll angle such that you would go further towards the wall, the system says, no, I can't let you do that, and clips it. So the red here is the pilot's desired roll angle, and the blue is the roll angle we're allowing. And basically we're saying, you're very close to the wall now, so there's no way I'm going to let you have a positive roll angle, because that will drive you into the wall. Whereas a little bit later, the pilot asks for a very positive roll angle here, and there's a little bit of clipping, but not very much. And that's because by that time, you've moved away from the wall.
I'm very much interested in this human-robot interaction. So where is the pilot come in your scheme? I didn't see that.
The pilot is providing that input.
That's the pilot.
Yeah.
Is it actually human?
In this scenario, we were simulating it. So there's somebody with a joystick.
Have a remote control?
Yep.
I see. Okay, thank you.
Yep. So, and this was a lot of thanks to Forrest. He actually built a system to do this, and it almost worked until the electronics fried itself.
Now, where do you normally get those curves for the pilot is doing?
So here, this is a simulation, and this right here is in simulation. The pilot was still using a joystick.
So that signal goes to that end?
Yeah, the pilot pushed the joystick up, and the system refused to respond to that. Okay. Now, the key thing I want to show you here is that this is 20 seconds. And we never had to invoke that LQR controller, even though our horizon, our capture basin horizon, was 1 second. So what we were doing at every point in time was guaranteeing that within 1 second, we can get you to this target set and invoke the LQR controller and guarantee infinite horizon safety. But we never actually had to do that because the pilot never sort of forced our hand. You know, if the pilot had kept on pushing, maybe eventually we would have had to do that. But it never occurred in this scenario, and we've never actually had it occur. Essentially what you're doing here is you're using the capture basin to say, look, there's this whole other set of states that might not be stable under your infinite horizon stability controller, but I can guarantee you can get there to the place you need to at any point in time, so let's just let you play around, and as long as you're not causing too much trouble, I'll let you keep doing this until I see that you're in danger of actually getting into trouble. So I'd like to show a demo, but I don't have time, and I forgot to bring my joystick. So we did do a simulation of all this, and the thing we learned from the simulation is that it's really difficult to use this system in practice, because the system just goes and clips your control whenever you're in a little bit of trouble. And you're doing this, and the system's clipping, and even though there's some visualization on the screen of what's going on, you have no intuition for what's going on.
It's just a regular joystick.
It's just a regular joystick. There's no haptics or anything like that. So, yeah, when I was down in May. So one solution might be a haptic joystick in this context, but there's a real limitation here, this thing here. Input clipping is not the right way to do this, necessarily.
Between the human reaction and the system.
Absolutely. And this project convinced me just that there is no way we're going to do this by invoking mathematics to figure out how to share the control between the formal methods and the human in the loop. Exactly. The mathematics is great for some things, but not so good for others. So I want to talk about the human in the loop control, and this is another project that I'm working on. We want to build a smart wheelchair because there's a lot of older adults, and there's more and more and more every day. Many of them are having mobility impairments, fortunately not Rujna, and many of them are unable to use a manual wheelchair, and you go to a long-term care facility and there's lots of people sitting around in manual wheelchairs that can't wheel themselves anywhere. And we know that if you aren't able to move yourself around, this leads to a rapid decline in cognitive and other health because you don't have that social engagement, you don't have that mental engagement that you get when you can move around. And this is a well-known phenomenon with anybody who has mobility impairment, all the way from infants all the way to older adults. Why now? Lots of people have done this. I think every robotics group in the entire world has at some point said, I'll build a smart wheelchair. But they have not been successful. And the main reasons I want to go after this is better sensors. That's why we're getting autonomous cars, is we've got cheaper, better sensors. And this part, that there was the opportunity to build a team that involved experts in mobility and older adults. And trainees, grad students and postdocs willing to talk to both engineers and medical professionals. And that is hard. I spent months working with a fellow from OS and OT, designing an experiment. And finally one day I said, I don't think you mean the same thing when you say variables as I mean when I say variables. And lo and behold, that was true, and that's why we were having such a frustrating time. So the project team was this Canwheel project, a cross-Canada collaboration for 6 years. It just wrapped up in, actually last month, officially wrapped up. And the goal was to enhance the mobility of older adult wheelchair users. And there were 3 questions we went after. How are they used now? How could they be used better? And how could they be better? That last one is the engineering part. How can we make smart wheelchairs? And what we wanted to build was a shared control power wheelchair that would provide assistance with collision avoidance and wayfinding. So 2 separate tasks that seem to be important. I don't know what to call this thing. I've been calling it shared control because it's not collaborative control because that seems to be swarms, and it's human in the loop. But the problem is when I talk to other people in HCI and say human in the loop, they don't mean the same thing I mean when I say human in the loop, so I'm not sure. Yeah, okay, so I could try semi-autonomous. Anyway, okay, so there were some earlier prototypes of this system, and you spend 3 years developing the prototype, and then you do a study, and you realize right at the beginning of the study that there's some feature of the system that doesn't work, and you really should have done it a little bit differently, but it's going to take you 6 months to redesign it, and you've got the study participants now, so you just have to test the system even though you know what the outcome's going to be. So instead we decided to do a Wizard of Oz study, and the idea behind a Wizard of Oz study is you have a human pretend to be the system you want to build. So in this case, we're going to have somebody with a remote control joystick standing behind the chair and pretending to keep it from crashing into things and overriding the actual joystick on the chair. Here's the tasks that we asked our older adults to perform. These are taken from a standard power driving assessment, power indoor driving assessment protocol. So if you're going to use a power wheelchair in one of these facilities, they will test you on, I think there's 23 tasks. And these 5 tasks that we selected actually test 8 of the things in the PETA. And so we had them do each of these tasks. And we did it under 3 modes. We'd already tested the no control mode, so them driving the chair by themselves, and that's not good. And so we tried one where the chair just stopped if there was an obstacle ahead, and they hated that. And so we tried 3 different modes. One was slow down as you approach an obstacle. One was turn away from obstacles. So this was direction control. And the third was the chair is just going to do the task. We're going to say, are you ready to go? And then when you say yes, the chair is going to dock under the table or drive into the elevator, turn around, and drive back out again. So this one represents the perfect autonomous wheelchair, because Bikram, our grad student, is way better than any autonomous system that you could build for piloting the wheelchair. And so this is sort of the best you could possibly do. And we wanted to see whether people would like that or whether they want something else. So here's the interface that Bikram was using, and I don't have time to show you the video, but this is an example. There's Bikram. He's standing behind the wheelchair, and they're trying to back in park the wheelchair. 10 participants in 3 long-term care facilities. Oh my God, is it hard to run user studies, particularly with this population, because each of them have their own setup in the wheelchair, and so we had 1 chair to do this study with, and setting it up takes more than an hour for each participant. Moving them into the chair takes about half an hour each time, and then you can run them for about an hour before they're exhausted, and so you have to get them back out of the chair again. And so we had A bunch of stuff in the beginning, some semi-structured interviews before and after they did the driving tests. Then they had at least one, sometimes two training sessions in the chair, and then 5 driving sessions where we were taking data. And each driving session comprised of 3 repetitions of each of the 3 policies, so a total of 45 trials for each participant, 450 trials in total, plus interviews. And this took 3 months just to collect the data because, as I said, each participant basically had the chair for 2 weeks solid. And so this was a lot of work, even though it's a tiny little population we ended up getting. We only got 10 people. So there's a lot of challenges here. Spectators, people came out at the long-term care facilities to see what we were doing because it was exciting. And so then the participant got sort of paranoid, and our cameras, which we had carefully set up so that we only had one camera facing the participant's face, so that was the only camera we had to worry about privacy issues with. All the other cameras were looking outwards. But of course, now we're seeing all the spectators. And so we can't release any of that camera data because we got all these other people that never signed a waiver. Yeah. Okay. Each driving session is a single task, 3 repetitions of each policy. And we collected qualitative data. And this is where all the interesting stuff happened. So think aloud while they were driving, and brief interviews after each policy and at the end of the session. We did get what I'm going to say quantitative data, which is some standard surveys. I'm not going to talk about the surveys because they actually didn't tell us anything. There's really no variation in the survey responses. And we did get this policy ranking, which I will show you in a few slides. So we've got sort of 3 categories: attitudes related to control, and essentially participants don't want to be taken out of the loop. That is by far the key thing that came out of this study, was evidence that they really don't want the chair to do it itself. And in many different ways. They want high-level decision-making. I want to go over there. I don't care if the chair thinks I want to go to lunch right now because it's lunchtime. I want to go there. Low-level decision, they don't want the chair to drive them up to a table because they're worried that the chair isn't going to stop in time and they're going to bump their knees. So they want to have low-level control over the chair. And finally, they want to be able to decide on the fly what level of control they want. Sometimes they're tired, sometimes they aren't. So they had a number of perceived benefits. A lot of it had to do with reduced workload, increased feelings of safety and confidence, reduced burden on other members of the long-term care facility, driving performance, and then concerns. And this one, the big one, was this lack of familiarity. Because it was a very short, they were only in the chair doing these trials for each trial only lasted a few minutes. So even with 9 trials in a day, they were actually only driving the chair for 20 minutes or so. And so we saw a big difference between their preferences the first day, whatever task they were doing on the first day, versus the last day. They started to have some confidence that the chair would actually perform properly. And I should point out, they very quickly anthropomorphized the chair. They forgot that Bikram was doing the driving. Now, not clear how much of that had to do with the cognitive impairment and how much of it is just something that people do in Wizard of Oz studies. They were told that Bikram was driving the chair, but they very quickly talked about the chair as if it was doing the work. So here's the critical thing. These are comparisons, and what I want to compare is between the fully automated, which is the darkest bar, and the other two, and in particular, the steering control. And you'll notice over here, overall, when you compare fully automated with steering control, the steering control wins. And in fact, it wins in every one of the individual tasks except the hallway task. And the hallway task was drive down the hallway, turn left, drive a little bit further, turn around, come back, and drive and make the opposite direction turn. And by the way, we're not going to tell you this, but when you make that second turn, we're going to throw a box in front of you. It's called the unexpected obstacle task. and we had a number of comments that sort of supported this fact that they actually find driving in the hallways to be exhausting. because there's always people in the hallways and dynamic obstacles, and it's not interesting. And so this one, they like the automatic, but other than that, they preferred the steering control. And in very few cases, for very few people, did they prefer the slow down. They wanted to maintain their momentum. Okay, yeah, small study, lots of issues with the participant group, but we were actually able to get them involved with a participatory design process, get feedback from them. And these are some design implications. And this is a paper in autonomous robotics, which is online already. One of the challenging things here is resumption of participant control after the intervention. That part, I think you might be able to tackle with traditional control things. The rest of this is very much more human factors. How are we going to modify those policies that we tested in this scenario? How are we going to modify them to do these things? How do we customize it and adapt it? This was a comment that every participant made. They want to drive themselves rather than be driven. And it's not at all clear what that means. That's a very fuzzy distinction. So we have to somehow get at the affective, what do they think being driven means? What do they think drive themselves means? And I don't have a good answer for that. So I think I've run out of time here. I won't be able to talk about, I won't be able to talk about the last one. But this one here is dealing with state uncertainty and noisiness in our numerical approximations, our sensor data, and stuff like that. And it turns out that using an algorithm called gradient sampling, we can actually get around a lot of this noisiness and produce nice paths. And so here's an example. There's an example of just driving a robot. This is a wayfinding problem. Driving a robot down this hallway to get to the goal location. Here's your standard particle filter running in ROS, and you can see it zigzags a lot. And here's one of the reviewers said, "Why didn't you try stochastic gradient descent?" Well, the answer I wanted to say was, because it's not going to work. But you can't say that to a reviewer, so we just tried it, and it doesn't work. And then here's the gradient sampling particle filter approach. So it gives you a nice straight path right down the middle of the corridor. And you can do it in more general cases. So this is what I find interesting about this algorithm. One of the things this algorithm produces is an approximation of the local subdifferential of the value function. And this is a really interesting construct because it's the set of directions, the set of controls you can apply and make progress towards your goal. It's not necessarily the optimal. There may be something in that subdifferential that's optimal. But we can use any control in this subdifferential and make progress towards the goal. And so maybe optimality is not the right thing. Maybe progress to the goal is the right thing. And I'm not sure where on that spectrum you might want to fall. Or maybe it's support for an action that the user is trying to do. So much thanks to the folks who have worked on the anesthesia project, to the sample data project, Claire, Mo, and Shahab and Forrest here at Berkeley. And Neil was a master's student now at Uber. Carolyn and Brandon were undergrads. And the wheelchair project is enormous. This is the Canwheel team from a few years ago. And lots of funding agencies. In particular, I'd like to mention AgeWell. So Canwheel wrapped up, and AgeWell is bigger and better. It is the biggest thing that they do in Canada, are these network centers of excellence. And AgeWell is Technology and Aging Network Center of Excellence. And it's a 5-year project, and it's the biggest NCE that's ever been done in Canada. And it's really an opportunity for students and faculty to work together in these collaborative setup. So my team is working on the smart wheelchair. We've got 3 engineers and 2 mobility experts working together, and we're doing an RCT starting next month on a new training algorithm that came out of the Wizard of Oz study. So, thank you.